Right, so there we go. Next we have, in an LR circuit connected to a battery of constant EMF E, switch S is closed. Okay, fine. If E denotes the, just will draw this LR circuit, you say. So this is L and R and constant EMF E. Okay, cool. Okay, t equal to 0, it starts working. If E denotes the magnitude of the EMF, okay, induced EMF across inductor, obviously, so like a voltage drop, whatever that means. Yeah, and I the current in circuit at any time t, then which of the following graph shows the, oh, so we just want in terms of I. Fine, so you can just use the Faraday's law or Kirchhoff's law, whatever you call it. So it says V equal to L times di by dt plus, yeah, that should be the thing, plus R I. Right, cool. But this term, it's not actually in terms of I completely, so we want more than just that, right? So we can solve this, probably that's the only thing we can do. So you have L di upon V minus Ri equal to dt, and then integrating that, you just get what, L -1, okay, -1 upon R, of course. This thing, natural log of, so you got V minus Ri, and initially, what's the thing, initially the inductor is not letting current pass through it, right? So it should be, this thing is 0, so this is just upon V, that's equal to dt, integral, that's t, cool. So you just got V minus Ri upon V, that's equal to e power negative RT by L. Alright, that's cool. So that's fine, and we just want what? Oh wait, the induced, yeah, like we want to find di by dt, isn't that right? Wait a second, just wait a second, isn't this thing the, yeah, this thing is the induced EMF, in fact. Well, that was very easy, it's just this thing minus Ri plus V. This is it, this is the function that we are talking about. So you literally just have E equal to V minus Ri. Yeah, that's the whole thing. So it's a linear function like this. Cool, that was weirdly easy. Okay, two identical inductors carry currents that vary, wait a second, yeah, where was I? Okay, two identical inductors carry currents that vary with time according to linear laws, as shown in the figure. Okay, which of these two inductors is self-inductance EMF greater? Wait, what? According to linear laws. Okay, fine. Yeah, that's fine. In terms of following, of these two inductance are yeah, if these are identical, of course, then just look at the di by dt thing, which is like, look over more like the negative slope. So this thing has more negative slope and this thing has less negative slope. That means this has higher voltage, of course. So first one has more. So self-inductor, wait, what? Self-induction EMF, of course, that's bigger. Self-inductance, that's equal, right? Yeah. So one is more, I think. Yeah, that makes sense, of course. Next, the current in given circuit is increasing with the rate 4 amps per second. Current in given circuit. Find the charge on the capacitor at any instant when the current is in the circuit is 2 amps will be. Okay. This is bad. So you got a resistor, an inductor, and that thing. Fine. So you just like straight up tell us that the current is increasing at a rate 4 amps per second. Oh, that's weird. Charge on the capacitor at an instant when the current in the circuit is this thing. What? 2 amps will be. This is problematic. Is this correct? I mean, like, how can you say that the current is increasing at a constant rate? First of all, is this even going to happen? Actually, let's just write the thing for this. You got V equal to Ri plus Q by C plus L di by dt, of course. Right, this thing is a constant. If we say that this thing is constant, right? Yeah, then you would just have Ri equal to, yeah, well, that will be weird. This doesn't make sense. You know what, just differentiate it with respect to time once again. So that will be like 0 equal to R di by dt plus I upon C plus L d squared I upon dt. And since we are assuming that di by dt is a constant, you can say like this is gone and this, wait, what? That makes no sense, because that's telling us that I is in fact constant, but that would mean that di by dt is also 0, which is not good, because yeah, that's just stupid. Right, this problem, it's just wrong, because this cannot happen in real life unless there's some external things that are, yeah, like something else that's also happening which they didn't tell us. I don't know, maybe like it's put in the magnetic field region and then the magnetic flux is changing, and because of that you got yeah, that could be happening. Of course, that could be happening. So charge on capacitor at an instant when the current is 2 amps. So you know, when in Faraday's law we say that integration of EDL equal to negative d flux by dt, over here this E, it can be either the induced electric field or the total electric field, because the total electric field follows this thing that sorry, the conservative that's like the electric field without the magnetic fields involved in it. That thing that would follow this law. And so if I say that induced electric field dl, and this is like, I don't know, not induced, right? So if that's that, and then we add these two, that will just give us the total electric field also follows this law, right? So over here we don't know what's happening with the total electric field, but we can figure out what's happening with the not induced electric field, right? Yeah. So this inductor over there, well, yeah, it has a 0 not induced electric field, I suppose. Is that right? I think so. Yeah, I believe that's right. It's, yeah, that should be the thing. Yeah, that's right. And its total electric field, well, that would also be 0, because like it's metal wires, and that would mean that V equal to IR, R is 0, so the total electric field voltage, that should be it's getting complicated. In any case, this is just 0. You got that field, that's actual field, it's not induced, and then there's a voltage drop over there, which is also an actual field, it's not induced, right? It's actually what is the integration of EDL at that point. All right, and then for this capacitor too, there's the same thing. It's just that this loop and the inductor has problems over there. Yeah, or you can say maybe like Li, that's our total electric field thing, if that makes sense. Yeah. This is stupid. course, this is not right. It's gonna be extra electric. This is just no. We cannot do it. Ri, that's not just the induced one, but that current also has the induced current in it, and that's stupid. We can't use this, just can't. So then how are we going to solve this? Because this question makes no sense. I'm just gonna cross this and say move on. All right, a coil of inductance 5 is joined to a cell of EMF 6 through a resistance 10 at time t equal to 0. The EMF across the coil at time t equal to natural log square root 2 is yeah, so we know that what was the thing? Yeah, negative L upon R, so it should be e power negative R upon L times T, V minus IR upon V. Yeah, that was the equation that we just got, right? Yeah, and just start putting things into that. So voltage is where's the cell? Okay, 6. So 6 minus current, we don't know. I think we want the EMF across the coil at what? It's trying to cell through resistance 10. Fine, so the coil is the inductance. So since we want the EMF, we essentially also want this current, or more like the yeah, that should make sense. Or we just can use that thing directly, that you have V equal to IR plus whatever is the the EMF because of that thing. Once again, we need to find what this thing is actually. It's like V minus IR, that's our E. This whatever this Greek E is, that's the EMF, the induced EMF. So yeah, like V minus IR upon V equal to e power negative R by LT. We're just going to use this thing. So 6 minus, okay, we want to find this thing. Instead of writing this, I can just write E. All right, cool. And what's this thing? It's 6. So 6 times e power negative R by L. Resistance 10, inductance 5, so it should be 2 times T, which is natural log square root 2. All right, that's cool. So the EMF at, okay, fine, just calculate this thing. 6 into natural log square root 2, huh? So this is that, and that will be 2, and this will be what? All that to the power of negative 1, natural log 2 power negative 1, which is 1 by 2. That's 3. 3 is the answer, I think. Yeah, next. A long solenoid of n turns has self-inductance L and area of cross-section A. Yeah, when a current I flows through the solenoid, the magnetic field inside it has magnitude of B. Okay, current I is, that's not problematic because B times A times N, that's our flux, isn't that right? Yeah. Oh wait, I put something wrong over there. Yeah, this is actually correct. VAN equal to LI. That's better. Okay, cool. And now what do you want? We want what's the value of B? That will be LI upon AN, which is no, we want the current. Sorry, we want the current. So I is BAN upon L. Yeah, which is which option? This option. Next, a long straight wire of circular cross section is made of non-magnetic material. Long straight wire of circular cross section, huh? Oh, like this is the wire made of non-magnetic material. The wire is of radius A. Okay, the wire carries current I, which is uniformly distributed. Okay, cool. The energy stored per unit length in the magnetic field contained within the wire. Yes, that thing. Magnetic field contained within per unit length, you say. This is problematic. So you want to find like what's du upon yeah, well, u is the thing, I think. Fine, so call this, for now just call this thing as u, call the energy as u. So we want du upon dA or dr, that's better, right? Yeah. Oh, no, something's wrong, something's just wrong. When we say length, we don't mean this thing, we mean this thing, right? Okay, cool. So we know that per unit volume the energy is half b squared upon mu naught. Don't ask me how this works, why this works. It's it's just what it is. Yeah, fine. Yeah, and it will contained within the wire. This is so complicated. Why should we even talk about this? Yeah, like whatever, fine. So if that's the thing, that per unit volume your energy is this thing, is that right? Yeah, I think it's right. It should be. Yeah. So if that's okay, then what's the volume that we're talking about? It is just pi r squared by a squared times h, but that upon h, because we want per unit length, and that should be the thing. Huh? No, something's not right over there. What's wrong? Just what's, it's not. Why is there pi in the denominator and not? Huh? We want in terms of current. All right, that's different altogether. Yeah, fine. So the current, magnetic field, which magnetic field are we talking about? Of course, this makes sense. Yeah, this is stupid because this density at this point is different than the density at this point, because the magnetic field itself is different. So really we are actually talking about integration of half 1 upon mu naught b squared. That should be the better thing to do. So that times the elemental volume, which would be like, say it's length h, I should say L, and this is R, so this volume will be 2 pi R times dr times L. Yeah, that's the thing, but we don't want L because 1 upon L, that's going to be there anyway, right? So we just want to integrate this thing from R equal to 0 to A. That should be working. And what is the magnetic field really? You can use Ampere's law to say, okay, cool, 2 pi R times B, that's, what's it like, it's mu naught times the current enclosed, which is pi r squared I upon pi a squared. That's right. So you can use that. So that tells us that this cancels with that, I guess. Magnetic field is mu naught upon 2 pi, it goes over there, r I. You can just plug that over there. Cool. So you're gonna have 4 pi squared, but that times 2 pi, that's gonna get cancelled, right? And you got r over there. Here you got r as well, so it's gonna be, wait, actually it's gonna be r cubed. We need more space for this thing. So this is what integration of, well, 1 by 2 mu naught, that's out. Magnetic field squared, that's gonna be like mu naught squared upon 4 pi squared r squared I squared r squared I squared, and then you got 2 pi r dr. Some stuff gets cancelled, 2 pi it's cancelled, and then you got 2 over there. This r, that's gonna be r cubed over there. Okay, this is no, it's 1 by 4 pi, right? So 1 upon 4 pi mu naught. Yes. Oh, but that's mu naught over there as well, so actually it's mu naught upon 4 pi integration of, yeah, that should make perfect sense, I guess. Like it's somehow similar to what capacitors do. Okay, whatever. So unit upon 4 pi. uh what else? You got this I squared over there, that's a constant, and this cancels, everything cancels except these things. So you got r cubed dr, that's gonna turn out to be r power 4 upon 4. So this is a power 4 upon 4. That's better. Yeah. uh okay, and now what? You just mess up some. Of course, I where's that a squared over there? There should also be a squared. So it's not just this thing, it's actually a power 4. Oh, there's another a power 4 over there. This cancels. That's nice. So it's mu naught upon 16 pi that times I squared. Well, that's weird. Okay, fine. Very weird. Actually, I have some things to do, so I have to go now. But I'll see you later. See you in the next video.